Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good. So here we are. So I'll just, given the short time, I'll just present two contributions in action recognition for videos. So what's action recognition in videos? So either we have a clip which is already extracted, and we want to do just perform action classification. So we have short clips in which we have actions, we want to classify them. For example, this would be the trajectory example where you want to classify things in making sandwich, feeding animal, and so forth. Or more difficult, you want to localize and search the actions in an entire video. So you have several hours of videos and you want to see where in the video the action is actually performed. And so obviously this is much more difficult because you have to have a much more discriminative descriptor. And so in this talk I present two recent contributions. One is on low-level descriptors, how to improve the low-level descriptors for representing videos. And the second one is a high-level model, a bit similar to what Ivan and Joseph and their students presented, by modeling the interaction between humans and objects, which can be done either in still images or here in this context in videos. Okay, so first, what is the idea behind the low-level descriptors? So here the idea is that we kind of borrow ideas from image description. So we want to do then sampling. We also want to do the sampling, so describe not every frame individually, but to track points over the video. So to use feature trajectories, so some workaround where they use, for example, KLT or SIFT trajectories. So here we develop or introduce an improved trajectory. And then obviously what you want to characterize, we want to characterize the space domain and the time domain differently. And so here the approach is we perform then sampling. We track the points over the frames using optical flow. So what we want is a good optical flow descriptor, which then allows us to track points for a short range of frames very accurately. And then the descriptors, they're based on an alignment with the trajectories. So we don't just take rigid cuboids, but we really align. So we have shown that this is important as well, can be evaluated, align the descriptor along the trajectory. So then we can either use classical descriptors based on Hog, SIFT-like features, optical flow histograms, or here in addition, we introduce an additional descriptor based on motion boundary histograms. Again, here just to give you an idea about the different trajectories, it's kind of obvious, but it's kind of nice to see as well. If you look at KLT tracks, which still many people use, actually nowadays you can really see that there are many outliers, they're noisy. It works well if you have large objects with good texture, but if you have small objects and no texture, then they just fail completely. You'll see this also in the context of our object tracks. Then similar, actually, the SIFT tracks, it's a nice idea, but again, they have a lot of outliers, a lot of spurious mismatches. You can really see if you have the feature tracks, there's a lot of noise in there. And so here, this is our dense tracks, and obviously you can say it's based on the optical flow. So here it's the optical flow for Fernback, which is an OpenCV. And it's clear, obviously, it depends on the quality of the optical flow, but if the optical flow here is good, you can really see that the tracks are very good. Okay, and then basically motion boundary descriptor. Again, it's a very simple idea, but the idea is basically, in many cases, you have camera motion. You want to be robust up to some point. Obviously, it's not completely invariant, but you want to have some robustness. So if you have background motion, for example, of the camera, which is a translation of the camera, you have all the optical flow, which completely pollutes your optical flow histogram. So just take the derivatives of the optical flow vector, you get rid of that. And similar, if you have motions in one plane, and you just take the derivatives, you have the relative dynamics of these regions. Obviously, if you have complex camera motions, it doesn't hold, but here it's really between two very close frames, so it's a good approximation. Okay, and then you can obviously use these trajectories and descriptors in many contexts. So here it's evaluated for the standard bag of features framework. You can obviously also use it. Recently we have used it with Fisher kernel representations where the results further improve. Or you can use these trajectories for clustering and segmenting out objects. So it's not just related to useful for the bag of features, but you can use it in different contexts. And so here, if you look at the results, so most importantly, you can see that actually these motion boundary histograms improve significantly of overusing optical flow. So in both cases, you have camera motion in the data set. So this is the Hollywood data set where you have short action clips which you want to characterize. You use your sports data set where you also have background motion. And then it's interesting to see is also that if you look here In this case, optical flow helps much more, while here, actually, for the sports videos, where the background is very dominant, so the actions are always, say, for example, diving is in a swimming pool and so forth, the background information is actually also very relevant. So that's interesting. And then what you can see here, it's maybe the most interesting thing, is you can really see that by using this dense or out-dense trajectory, you improve significantly over using KLT or SIF disk trajectories.
Is it just due to the fact that KLT or SIF is at interest points instead of being dense, or is your tracker?
Well, I think it's, you have seen it, right? It's like it's more noisy probably. That's the main reason. I think if the tracks were perfect, right? The KLT tracks were perfect, and then basically could propagate them around. So it's both. Basically, it's the denseness, which gives you more information, as you have seen. Basically, for images, if you use interest points for category recognition, you lose information, you lose a few percent, and then the KLT tracks there. So I'll come back to that in a moment. They're really intrinsically noisy. So they have, I mean, basically, if you want to track small objects or things like that, you really want to have the optical flow, which is actually more robust to these kind of noisy outliers. So basically, in this case, matching interest points gives you one clue, but you want to also use the low-level signal. So basically, the best approach is or one good approach for optical flow is the Brock's algorithm, where you combine the lower-level measures with the high-level interest point measures. So you want to have both together and then do some optimization over the whole thing and have it locally integrated. While interest points, they only look at two adjacent frames and they don't take into account all this information. So you're kind of losing out on the information which you could get.
And the number of tracks is the same, or roughly the same for all three, or?
No, that's not exactly the same. So that's something which we're now experimenting with. If you take
roughly, or so like dense would it be twice? 3 times
yeah,
more?
but dense I think twice or 3 times more. So that for dense, I've removed the slides because I have not much time. But dense, we also do some pre-filtering, right? If there are points where there's absolutely no information, they're sitting in completely homogeneous regions, we just remove them, right? Because there you cannot track, right? So you have also, and you have a grid step. So basically, you can evaluate the performance over the grid step, which is then the same thing. You can just remove the grid step to get the same number of points. So I don't have the numbers exactly in my mind, but we did the experiment, so I can actually dig them out, because you can just subsample. I mean, it's not dense, it's just some subsampling on the grid, right? So you can just remove it further till you get the same number of points for KLT. KLT, you can vary them a bit as well. So.
And then you still get improvement?
Yes, you still get improvement, yes. Okay, and then basically also the results compare favorably to the state of the art. So for all the state of the art data sets, we outperform existing approaches. I'm not showing the slide now. And then basically we have seen, so they really outperform any of the existing approaches which are around today included. So there was this paper at CPR there this year where they learn this based on dense trajectories and depth. So this approach where they learn the hierarchies automatically. So our approach outperforms that as well. The motion boundary descriptors perform very well. They're robust to camera motion, and the algorithm is very simple. It's available online, and you can just run it and try it out.
Compare the Taylor and Weber, Seth-Taylor and Weber, the guy.
Yeah, we haven't. So we also didn't use the Brock's tracks. So that's something we tried to do, and actually they're so slow. All these algorithms, they're so slow that right now we're kind of trying to speed those algorithms up. I think they would give you a further boost, right? So if you have a good optical flow, the better the optical flow is. I think I get the feeling. But really the results we did on a very, very small subset for Brock's tracks, it takes about a minute to run per frame. So if you want to run it on a real data set, it's just too slow. So I don't really know. We're currently kind of looking at that, if you can speed it up a bit to have some compromise. Because otherwise you could test it. So we did a comparison on a very small data set, where there it's obviously even better if you have a better optical flow algorithm, so you can still improve a few percent, but then you really slow down your complexity. I mean, 1 frame per minute, if you look at the video, it's just not possible, right? So you have to do something about speeding that up further, or I don't know, something we're currently investigating. Okay, and then the second thing, so for obviously what you really want to do is you want to model the interaction between the person and the object. So again, I'm showing coffee drinking, but I have other data sets as well. You'll see in the end chopping a banana. So hold on till the end and you'll see. And anyway, you can see here, this is done automatically, right, on the test set. We detect the humans automatically, and then we also get the cup and really see that the guy is drinking. So that's really, I think
it could be tea, actually.
Yes, yes. And what's actually nice is, if you look at the beginning, even if you drink out of this mug, you still detect it correctly, and I guess that's due because what our descriptor of the object, it captures some part of the hand, right? So it's important actually that it's not just the object, but the hand holding the object actually. And that's why you also having this big teapot, which is kind of nice, right? That you learn a cup detector, you still detect pots. And so,
nice on that.
what?
You learn a cup detector and it detects random stuff and it's good like that. You learn a cup detector but you still find something else and you say it's good.
I say it's good.
It's supposed to find a cup.
It's a similar, okay. It's a similar shape. So, okay, wait till I explain the approach. But basically what it does, we have a very loose detector and tracker. So basically it detects many objects because cups in these images, for example, or whatever you'll see telephones, they're very small, right? So if you want, if I look at Andrew Blake here with the cup, so the cup is very small, and we all know object detectors, if the objects are small, work not as well, right? I mean, you must admit this as well. So what we do is we detect many of the cups. So we have many cup hypotheses. So you have 100 cup hypotheses per image. We track them. And so what we do is we keep many of these potential cup tracks, right? And so then we have the human detection. I'll get back to this in a moment. It's pretty reliable. Again, there might be some false positives, pretty reliable. So then we have a temporal model which allows to filter out all the cup tracks which are not behaving like this. Okay? So that's probably why, even if this bad cup gets a relatively low score, you're still able to get this motion information and filter it out. Okay. And also it's not performing perfectly 100% of the time, right? So there are some errors. Anyway, so what works well here is our human detector. So we have a good human detector which we combine with, for example, Brock tracks. For the humans, it's not so important. The tracker is not so important because you have, in general, large surfers. And then basically integrate this over time. You get really good human tracks. For the object tracks, as I said previously, it's much harder. So in the beginning, we used KLT tracking, and it doesn't track at all because it just loses these small cups all the time. There are not enough points in them. So what we use now is this Brock's optical flow, which really allows to follow the cups. So what you do is have a combined detection and tracking framework where we detect cups and track them over the time with the Brock's tracks, glue those together. And we get they're not perfect, they're far from perfect. What we do, as I said before, we extract a large number and filter them out. So we have a large number of these pairs, and then we have some spatial, temporal, and relative location descriptors which allow to filter out incorrect tracks.
How do you know which objects to track?
That's given. So the human detector is learned, so we have a human detector which we have trained.
Yeah, person makes sense.
And for the cups we take, so in the training we have annotated the cups. In the training videos we have annotated 1 cup per training video. And then we track them automatically and use that as additional training examples. So, and it's not done automatically. We have developed for static images, we have developed an algorithm which actually selects the objects automatically. So if you have many, so that's something you could do as an extension. If you have many videos where the human drinks from a cup, you could say that basically what you want is basically, what you're doing, some kind of co-segmentation. And we have done that for static images. Here, the cups, they're so small that it's really difficult to track them and to learn it automatically. So for now, we're still in this weekly supervised scenario where we annotate 1 cup per training. And there are not that many training examples, so there may be, I don't know, Ingvar knows better. I think there are around 30 training videos for which we annotated the cups, so it's really 30 boxes. So it's not very difficult. And okay, and then we combine this interaction descriptor with some previous work which was done with, where's Andrew? He's gone. Which was done with Andrew. So here we have this track, and we have a set of low-level features within the track based on 3D Hawk descriptors which characterize the motion, some kind of optical flow inside the track. The track follows the person, and there's inside the track we have the small cells where we characterize the motion. So it's a more rigid descriptor, right? This is a more rigid descriptor, while this is really a flexible descriptor which can model very, very many variations of the motion. And then, not to show results on the coffee and cigarettes dataset, I'm now showing the results on the Gupta dataset. It's one of the state-of-the-art datasets for interactions. And you can see here on this dataset, the interaction classifier performs extremely well. If you then combine it with our hog track classifier, you have 93% performance, which is the same as Gupta. While Gupta, he uses a much more complex model. He uses, for example, the fact that it's a static background and all that, which we don't. So really, and he uses much more training data, so has like annotations for all the human poses for the objects. So, and anyway, if you look at the results, we have only 2 misclassified examples, so we're kind of saturating on this data set. And then we also tried it on the Rochester daily activities data set. So there are 150 videos of 5 persons. What they do is they leave standard scenarios, leave 1 person out test scenario. And so you can see here again, the objects are very small. So again, it's pretty difficult to detect them. And you can see here that our interaction classifier outperforms approaches which use only low-level features. And then if you use the full model using the 2 descriptors together, we outperform the state of the art. And what's really nice, if you look at this chopping banana, you can see here that we can really follow the knife and we learn how to chop the banana. So basically our approach, if you look at the results here, we're better, but what's measured here, it's only classification. So they don't measure at all if the object is localized correctly, because what you really want to do here for a good evaluation is really to say, do we detect the objects correctly, right? Because that's something you really would like to know if you really detect the object. Because if you detect the object here, then basically your model is just doing something completely different and it's wrong, right? So that's not what the current approaches are evaluating. So, okay. So in conclusion, we have seen that basically our human object interaction descriptors outperforms the state of the art. It's complementary to this 3D hog tracking descriptor, and it obtains excellent performance. And like as a message, the tracking algorithm is really important. So something which I didn't expect in the beginning, but something which we found for both approaches, actually good optical flow or good tracking is important. Okay, thank you. I think I didn't overrun in time. So.